All right, in this video, we're going to go through solubility rules, and then we're going to do a few word problems where you are going to write out the equation from the description, predict the products, and then balance it. So let's dive right in with solubility. Solubility determines the amount of solute that can dissolve in a given amount of solvent. So we have a solute and a solvent. Solvent might be a word that you've heard before. It's used a lot in cleaning supplies. A solvent dissolves or busts grease and grime. So a solute is what's being dissolved. The solvent is what's doing the dissolving. So like Kool-Aid, for example, the powder is our solute. The water is the solvent. Now, something can be soluble, which means it can be dissolved, or it can be insoluble, which means it cannot be dissolved. Our Kool-Aid powder, for example, is soluble. Salt is also soluble. We can put it into water and it dissolves. Sand is insoluble. It just kind of goes to the bottom. Or metal, for example, if I put a penny into a glass of water, it just kind of goes to the bottom. So those are insoluble. All right, when we write out our chemical equations, we're going to include the states of matter. Okay, now, some of these you may have seen before, like solids, liquids, and gases are all very common, probably taught in elementary school, middle school. You've seen these before, but aqueous might be a word that you're unfamiliar with, and that means that something is soluble. It's been dissolved in water. Okay, so a couple rules here. Metals are always in the solid form. Acids are aqueous, meaning they're dissolved in water. And then we have H2O, which is going to be a liquid. Okay, so we're going to write out some word equations here, and then we're going to be using a solubility chart to help us with the states of matter. So this is a solubility chart that's on the Flint Scientific website that we're going to be using. I love this chart because it is very easy to follow. So let's begin. So it says predict the products when copper 2 chloride reacts with potassium hydroxide. Okay, so we have copper 2 chloride, so that means copper 2 is copper with a positive 2, and it's chloride, which is chlorine. Chlorine is -1. And then we have potassium, which is +1, and hydroxide, which is -1. Okay, so this is going to be a double replacement reaction because we have two compounds. So let's go ahead and let's write out our left side of our equation. So we have copper 2. So I need 2 chlorines to balance here. All right, I'm going to leave some space for the states of matter. We'll get to that in a second. We have potassium and hydroxide, so that's just going to be KOH. Okay, on the right side of our equation, copper is going to go with hydroxide. So it's going to be Cu and then OH2. And then potassium is going to go with chlorine. Okay, so now we're going to go back and we're going to add in the states of matter. Okay, so let me show you how to use this chart. So copper and chlorine, for example, I'm going to find copper. It's listed in the transition metals, and I'm going to go down to where it says chlorine. Notice it says it is soluble. So if it's soluble, I'm going to write the word aqueous. Okay, KOH, I find potassium, and I drop down to OH. SOL means soluble, so it's going to be aqueous. Copper and hydroxide is next, so copper. And I go down to hydroxide, so it says insoluble. Okay, if it's insoluble, that means it's going to be a solid. And then we have potassium chloride. KCl, if I go down, it says soluble, so that means it is going to be aqueous. Okay, so there's our equation written out, and we have the states of matter. Now we're going to balance. All right, so I have 1 copper, 2 chlorines, 1 potassium, 1 hydroxide. On the right-hand side, I have 1 copper, I have 2 hydroxides, 1 chlorine, 1 potassium. Okay, so to balance this, let's start with the hydroxide. So let's put a 2 here. Okay, so that's going to multiply to our potassium. That makes that a 2. The 2 also goes to hydroxide, so that'll make that a 2. Okay, and now I need to balance my chlorine and my potassium, so let's put a 2 here. So that 2 multiplies our potassium by 2, and it also multiplies our chlorine by 2. And look at that, we're balanced. Okay, so there's our first equation. We predicted the products, we predicted the states of matter, and then we went ahead and balanced it. Let's move on to the next one. So it says predict the products with sulfuric acid reacts with sodium hydroxide. Okay, so sulfuric acid doesn't have the word hydro in it, so I know it's not just sulfur. It's going to be sulfate, okay, because the ending of our acid is ic. Okay, 8 turns to ic with our acid. So sulfate, so I have hydrogen and I have sulfate. So this is -2. Hydrogen is +1. Okay, and it's saying it reacts with sodium hydroxide. So sodium is Na, and sodium is +1. Hydroxide is OH, -1. Okay, so since we have an acid and we also have a base, this is going to be an acid-base reaction. So I have H2 because 1 hydrogen and, hydrogen is +1 and sulfate is -2. So this is going to be H2SO4. Okay. Sodium and hydroxide are both magnitude of 1, so I'm just going to put those together. Okay, so with an acid-base reaction, remember our products are going to be water, and then our leftovers, so our sulfate and our hydroxide are going to go together. So, no, I'm sorry, not our hydroxide, our sodium. Our sodium and our sulfate are going to go together. Okay, so Na is +1, and then sulfate is -2, so I'm going to need 2 sodiums to balance with my sulfate, just like that. Okay, so let's go through and predict our products. First of all, H2SO4, it's an acid, and that's always going to be aqueous. All right, our base, NaOH, let's go ahead and look at our chart here. So Na is right here. If I drop down to OH, it says soluble, so that's going to be aqueous. H2O is always a liquid. Na2SO4, so Na2SO4, it says soluble, so aqueous. Okay, let's go ahead and balance this. So we have hydrogen, we have oxygen, we have sulfate, we have sodium. Okay, so when you're counting up your hydrogens, be careful because, like on the left-hand side, hydrogen is in both our sulfuric acid and it's also in our sodium hydroxide. So I have to count it in both places. So I have 2 from my acid and I have 1 hydrogen here in my base. So that's going to be a total of 3. When I go to count the oxygens, I don't want to double count the oxygens. So meaning I don't want to count the oxygen that's in the sulfate because I'm separating the sulfate from the other oxygens. So 1 oxygen here, 1 oxygen here, and then oxygens by themselves, I have 1 here, and then I have 1 here. All right, on the right-hand side, I forgot to count our 2 hydrogens right here. And then sodiums, I have 1 here, and I have 2 here. All right, let's go ahead and balance this now. So I'm going to start with my sodiums. You want to balance hydrogen and oxygen last just because they are in in this case, hydrogen's in 2 places. Oxygen can also be in 2 places sometimes, so we're going to balance those last. So to get my 2 sodiums, I'm going to put a 2 in front of my sodium hydroxide here. So 2 times the 1 sodium makes that 2. 2 times the 1 oxygen makes that 2. 2 times the one hydrogen makes that 2, but don't forget, we also have this hydrogen right here. So 2 times 2 is 2, plus the existing 2 makes this 4. Okay, so everything's balanced except for our hydrogen and oxygen. So on the right-hand side, I'm going to put a 2 right here. 2 times 2 makes that 4. 2 times 1 makes that 2. And we are balanced. Okay, so that was an acid-base reaction. Now let's take a look at this one. It says predict the products when aluminum reacts with iron 2 chloride. Okay, so we have aluminum. Aluminum is +3. Okay, and then it's reacting with iron 2 chloride. So iron 2 means that the iron is +2, and we have chlorine, which is -1. Okay, this is going to be a single replacement reaction because aluminum is by itself, and since it's a cation, it's going to pair with chlorine, which is an anion, and iron is going to be kicked out. So let's write the left-hand side of our equation. So we have iron by itself, and it's going to react with iron chloride. Iron is 2, chlorine is -1, so I need 2 chlorines to balance. Okay, on the right-hand side, again, aluminum's going to bond with chlorine, so I need 3 chlorines to balance with my aluminum. Since each chlorine is -1, aluminum is +3, and then like I said, iron is going to get kicked out. Okay, aluminum and iron are both metals, so I'm going to write that they are solid. Let's go look at our chart here. So we have iron and chlorine. So here's iron and chlorine. It says soluble, so that will be aqueous. Aluminum and chlorine. So aluminum and chlorine, it says soluble, so that will be aqueous. Okay, so there are our states of matter. Let's go ahead and split this in half, and we're going to balance this. So we have aluminum, iron, chlorine, aluminum, iron, chlorine, 1 aluminum, 1 iron, 2 chlorines, 1 aluminum. We have 3 chlorines here, and 1 iron. Okay, I can tell you right away that we're going to have to do something tricky because for chlorine, we have a 2 and a 3. 2 and a 3. So we're going to need to get to our least common multiple of 2 and 3, which is 6. Okay, so to get our 6 chlorines on the left-hand side, I'm going to put a 3 here. 3 times our 1 iron makes that 3. 3 times our 2 chlorines here makes that 6. On the right-hand side, to get our 6 chlorines, I'm going to put a 2 here. 2 times our 1 aluminum makes that 2. 2 times our 3 chlorines makes that 6. Okay. Next, let's balance our irons. So I have 3 on the left, I have 1 on the right, so I'm going to put a 3 right here. 3 times 1 makes that 3. And then the last thing I need to do is balance my aluminums. So if I put a 2 right here, 2 times 1 makes that 2. Look at that. We are balanced. So we went through how to take a word problem and predict the products and then balance it. We also went through the solubility rules, and I used Flynn Scientific's table of common ionic compounds. It's on their website. It's fantastic, breaks everything down, and it's pretty easy to follow. So got all that. Good luck and have fun predicting and balancing reactions.